And it's a pleasure to be here, to see so many old friends. Okay, so I'd like to tell you in this talk about experiments we are doing at Princeton with studying cold atoms in optical lattices with a quantum gas microscope, in particular focusing on the Fermi-Hubbard model. So just a quick overview on the idea behind our research. So what our experiments are all about are understanding strongly correlated materials. So there are many strongly correlated materials people like to study in condensed matter, things like high temperature superconductors or topological phases of matter or quantum magnets. And usually understanding these materials is, it's a problem at the frontier of condensed matter physics. They're very hard to understand. And if you're a theorist, one of the first things you would do is to try to model these materials with some simple model that captures the essential physics. For example, for a high temperature superconductor, a common model that's used is the Fermi-Hubbard model. For maybe this compound there, you can use a quantum spin chain. So of course, in this step, there might be a lot that goes wrong if you miss the ingredients that give you the important physics. But then once you have these models, you are still faced with the challenge of solving these models in the sense of getting something like the ground state phase diagram or figuring out the dynamics within this model. Because these are quantum many-body systems, so the complexity of the problem scales exponentially with the system size. So the idea behind our work is to use cold atoms to realize some of these models exactly in the lab, and essentially use these cold atom systems as quantum simulators in the sense first envisioned by Richard Feynman a long time ago to get at properties of these models. Okay, so what we're using is cold atoms in optical lattices. And these look a lot like the electrons in the ionic lattice of a solid. However, this is an enlarged model for condensed matter. So essentially, the spacing between the lattice sites is on the order of a wavelength, on the order of a micron, because it's set by the wavelength of light. Whereas in a solid, you have an angstrom, so you have an enlargement of 4 orders of magnitude. And so these systems have a lot of advantages in doing these quantum simulations. We can realize very clean systems with no impurities in them. And we have complete control over the microscopic parameters, things like, say, the tunneling between nearest neighbor sites or the interactions on a site. We can control all these things in the lab. And when we write down the Hamiltonian for these systems, we really know the microscopics of the Hamiltonian. So we know that the Hamiltonian we are writing is correct, as opposed to in the condensed matter case where it's probably an approximation of what's going on. And then going back to this idea of an enlarged condensed matter model, what this buys us is that the dynamics are really slow, typically on the millisecond time scale. So it's easy to access in the lab. And most importantly for this talk, this large spacing makes it possible to use optical techniques to image and manipulate the atoms. Yeah?
So if you don't know what the Hamiltonian of the condensed matter system is, how do you know that the cold atom system is a good analogy?
We don't. We'll just see what properties emerge from the Hamiltonian we see, and let's see if the properties map to the macroscopic properties that we see in the condensed matter system. Okay, so here's the Hamiltonian I would like to focus on. It's the Fermi-Hubbard model. This is a Hamiltonian that has been studied theoretically over several decades, mostly motivated by a proposal a long time ago by Phil Anderson that this Hamiltonian might capture the essential physics of the high temperature superconductors. And we still don't know if that's true. Okay, so the Hamiltonian describes the physics of 2 species of fermions. These are these blue and red species here that are essentially hyperfine states, 2 hyperfine states of an atom. And these atoms live in a 2-dimensional optical lattice. And all they can do is just tunnel between nearest neighbor sites, or whenever 2 opposite spin fermions land on the same site, they interact with a strong interaction, U. Okay, so that's described by the tunneling is the first term in the Hamiltonian, and then the interaction, which we can control, say, with Feshbach resonances, is the second term. And we can realize this model very cleanly with these atoms in optical lattices. And we can vary the parameters over several orders of magnitude. So you can change the tunneling using the lattice depth. You can change the interactions with Feshbach resonances. And you can change this by a few orders of magnitude. So of course, this Hamiltonian, we don't know its phase diagram. Despite the simplicity and decades of work, we still don't know what the low temperature states of this Hamiltonian are. But if indeed it describes the Coop rates, then we can look at the Coop rates for guidance for what the phase diagram we might expect looks like. So here's a phase diagram of the Coop rates in the temperature and doping axes. And at high temperatures, well, at temperatures below the interaction energy, you start to get into a Mott insulating phase. So this is kind of high temperature in this phase diagram. And then as you start to lower the temperature, if you are undoped, you get into an antiferromagnetic state once you cross below the superexchange energy scale. So that part we understand pretty well theoretically. But then once you start to dope, that's where the theory gets really hard. And there's a lot of interesting phases that people see in the Coop rates, pseudogap phases, strange metals, incommensurate antiferromagnets, D-wave superconductors. And it might be possible that all these exciting phases are there for us to discover in the Hubbard systems. So that's where we're heading. OK, so let me just give you the state of the art in where cold atoms are. So after pioneering work in the groups in Munich and in ETH Zurich, where they observed Mott insulators of fermions and optical lattices, later work in the groups of S. Tillman Esslinger and Randy Hewlett observed initial signatures of antiferromagnets, short-range antiferromagnetic correlations, using different techniques. So for example, Randy Hewlett used a technique where they just scattered light off the atoms in the optical lattice, and they could measure a signal of this initial antiferromagnetic correlations. But more recently, in 2016, we have a new tool coming online, these fermionic quantum gas microscopes that have appeared in 6 labs now, which are capable of resolving the imaging individual atoms in the optical lattice in a 2-dimensional system. And they're able to directly image these states like Mott insulators and antiferromagnets. These groups are working with different atoms. So 3 of them are working with potassium. The other 3 are working with lithium atoms. My own group works with lithium atoms, and I'll be showing you some of our results. OK. So here's an outline of my talk. So I want to tell you about about experiments we've done in equilibrium systems and experiments we've done in linear response dynamics. OK, so on the equilibrium side, we've tried to push the Fermi-Hubbard systems into new regimes. So we've looked at repulsive Hubbard systems, but now we've added a new ingredient, which is spin imbalance. And then I'll tell you another story about attractive systems with attractive interactions. And these new ingredients I'll show you, lead to new physics, things like candid antiferromagnets or charge density waves. And then in the second part of the talk, I'll switch to dynamics, and I'll tell you about experiments we've done on charge transport in the Hubbard model. And there we saw signatures of bad metallic behavior. OK, so let me first briefly give you a tour of our Princeton Fermi gas microscope. So as I said, we're using lithium atoms. So up here, you see a picture of the lithium atoms loaded into a magneto-optical trap. This red blob in the center has about 1 billion atoms cooled with laser cooling down to millikelvin temperatures. From there, we load into an optical dipole trap formed by crossed beams. So there we get a few million atoms, and we can evaporate this gas degeneracy optically. And at that point, we get a degenerate Fermi gas of lithium atoms in 2 hyperfine ground states. And they are living in 3 dimensions. So we want to study the 2D Fermi-Hubbard model, so we have to convert this into a 2-dimensional gas. So the first thing we do is load into a light sheet, which is essentially a very anisotropic trap. But it's not tightly compressed enough to get into the two-dimensional limit. So to get into a proper 2D limit, what we use is loading this cloud into a single layer of an optical lattice. So that's formed by the intersection of these two green laser beams. Those form a set of a stack of pancakes in the vertical direction. And we have the ability to control in real time the angle between these laser beams. Okay? So that controls the fringe spacing. So when we load, we are at a very large fringe spacing. And so we can load the entire cloud into a single layer. And then we increase the angle between the laser beams to compress the traps. And then we end up in a 2D regime we can enter the 2D regime with about 20,000 atoms or so. So by 2D, I mean here that in the vertical direction, the motion is completely frozen, as in the temperature, the interactions are all less than the spacing between the harmonic oscillator levels. So we're in the ground harmonic oscillator level in that direction. Okay, so here I show a picture of the cloud from the side, where you can see that we can load a single layer. And if we want, we can load multiple layers. But all the experiments I'll be telling you about are within a single layer. Okay? All right, so at that point, we have a two-dimensional gas. Now we'd like to make it into a Fermi-Hubbard system. So what we do is we want to introduce a lattice potential. So that's this red beam here. So this configuration, so essentially the beam goes around like this and bounces back. This is a configuration that was actually studied a lot by Trey. And you can get a lot of interesting geometries depending on the polarization of the light. But in our experiments, we're just using a vertical polarization. So what you get is essentially a lattice geometry with a relatively large lattice spacing. So here we're using 1064 nanometer light, and what you get is a 750 nanometer lattice spacing. And the advantages of this geometry are that you can get a very deep lattice because all four beams with a vertical polarization would interfere. That's very good for later on for the quantum gas microscopy because we need to have a very deep lattice to pin the atoms during imaging. And at the same time, using this configuration allows us to get this relatively large lattice spacing so we can image the system with a low numerical aperture objective, relatively low, of only about 0.5. So it's not so challenging to do the single atom imaging. And now, of course, this comes with a small hit on the tunneling. But since we're using a very light atom with lithium, then that doesn't matter so much. We still can be adiabatic to prepare low temperature, low energy states. Okay. So now, essentially, we're loading the system adiabatically from this Fermi gas into this lattice. Hopefully, we've prepared some interesting correlated state. At that point, we want to image the state. So what we use is, so we could just shine some resonant light on the system and then collect the fluorescence on a camera. But if we do that, we find that very quickly the atoms start to get, they heat up very quickly and they would start to hop between the sites. So we would lose the spatial information. So instead, what we do is we eliminate the atoms with laser beams that are in a Raman cooling configuration. Okay? So in this configuration, the laser beams initially heat up the atoms because the atoms are starting close to the ground state. They initially heat them up, but eventually they reach an equilibrium temperature, which is well below the lattice depth. Okay? So that means that the atoms are now, they remain on their respective sites, so we get a good reconstruction of the density on a site. And so we can collect in about a second or so about 1,000 photons onto a camera, and so we can get with good signal to noise this density, and during that second we get a hopping rate and loss rate on the order of 1% level. Okay, so that's the system. Let me show you now some of the pictures we get. So here's a picture of a cloud that so the atoms are sitting in a harmonic trap due to the Gaussian profile of the laser beams. And we can adjust the filling in the center of the trap by controlling the atom number in the trap. So here we've chosen the conditions so that we're working at strong interactions. And the conditions in the center are such that you get a Mott insulator. So by Mott insulator, I mean we have one atom per site. So essentially, the strong interactions suppress number fluctuations. And you end up with 1 atom per site in the center, but of course the density drops towards the edge of the trap. So on the outside, we get a metallic phase. Okay? So now if we increase the atom number even further, so each one of these little green dots here is an atom, and here the resolution of our system is very close to lattice spacing, so you can't quite see the atoms, but you can see when you have a missing atom, you can see it here, or here, or here. But with the reconstruction algorithm, we can actually fit where all the atoms are, because we know essentially that we're using this square lattice, so all we need to know is the phase of the lattice. Okay, so now if we increase the atom number further, we get a band insulator in the center of the trap. So there we have essentially an up and a down spin on every site. And during this Raman cooling process, within the first few photons, you get light-assisted collisions that eject pairs of atoms. They form molecules and they disappear very quickly. So we don't see any atoms in the center where the band insulator used to live, but we still see the Mott insulator shell on the surrounding it. Okay. So that's the kinds of pictures we can get. And now I'd like to tell you about this first experiment we've done, where we've looked at what happens to a Fermi-Hubbard system in the presence of a magnetic field, a Zeeman field. Okay, so in a condensed matter system, what you would do probably to introduce a Zeeman field is, let's say you have a 2D system. You would probably just put a field in the plane of the atoms to avoid any Lorentz effects. Of course, our atoms are neutral, so unless we play Ian's tricks, we're not going to get Lorentz forces. So if we want to introduce just a pure Zeeman field, one easy way to do it is to just imbalance the population during evaporation. So what we do is we introduce a spin-dependent potential during the evaporation that evaporates one of the spin states preferably compared to the other. So let's say we're losing more of the red atoms compared to this green atoms. And we end up with this population imbalance. And now because we don't have any spin relaxation in our system, whatever spin polarization we have will persist throughout the experiment. So we can pretend that it's coming from an effective Zeeman field. Okay? Okay, so now we have this, we've introduced this Zeeman field, and we have a Hubbard model. And the Hubbard Hamiltonian is something we already don't understand very well. So we've just added another ingredient, so it sounds like even a bigger mess. So we thought, okay, maybe a good place to start would be to go to a corner of the phase diagram where we understand things a bit better, which is working at half filling. So half filling means working at an average density per site of 1 atom. Okay, so there at half filling, the Hubbard Hamiltonian can be approximated by a Heisenberg Hamiltonian, which is this term here. So essentially, what you do is, at strong interactions, you ignore the quantum fluctuations of the density, and you pretend you have 1 atom per site, and then those the spins are interacting through super exchange processes, and you get an antiferromagnetic coupling between the spins. Okay, so you get a nearest neighbor interaction. You get this Heisenberg model, and now we're adding to that this effective field, where H, the effective field, is essentially the difference in the chemical potentials between the up spins and the down spins. Okay, so we could ask, what is the phase diagram of this system? So even this Hamiltonian, quantitatively, we don't know its phase diagram exactly, but we know roughly what it should look like. So here it is versus temperature and field. So at high temperatures, you get a paramagnet, and as you get to lower temperatures, you get into an antiferromagnetic phase. Now, if you were at 0 effective field, so a spin-balanced system, 0 polarization, and you start to lower the temperature, you go down this axis, you would expect at some point to start forming antiferromagnetic correlations. And these correlations, the Merman-Wagner theorem tells us that the correlations decay exponentially. As you cool the system, this correlation length diverges, but you never get into an ordered phase. If you introduce an effective field, then there's actually, so what you do is, so at 0 field, you have an SU2 symmetry. So you get an isotropic antiferromagnet. The Néel vector can point anywhere in space. But now once you break that symmetry with an effective field, you've reduced the order parameter to U1. And so now you can form vortices and anti-vortices of the spin. And those, what you can do is you can have a BKT transition as you lower the temperature into the scanted antiferromagnetic phase. Okay? So in the scanted phase, essentially, the idea is that you have if you want to take advantage of the antiferromagnetic correlations, you can have your spins pointing like this, or you can have them pointing like this. But it's better to point them orthogonal to the field like this. Let's assume the field is along Z. It's better to have them point orthogonal to the field because this way they can cant towards the field to relax their energy. Okay? So in the scanted phase, you preferentially have your antiferromagnetic correlations in the plane orthogonal to the field. Okay, so this transition happens roughly at about 15% of the tunneling energy. In our experiments, when we did those experiments, we were at the lowest temperatures we could access were about 45% of the tunneling energy. Currently, we can reach about 30% of the tunneling energy. So it's a factor of 2 to 3 above the transition temperature. But we can still see precursor correlations to this phase transition. So what we'll be looking for is precursor correlations to the scanted antiferromagnet. Okay, so first, before I show you the spin correlations, we can take a look at the density in the system. So you see here, here's the minority cloud, here's the majority cloud in red and green. This is a pretty spin imbalanced cloud, and here's the total atom number. So these are all just imaging just the singles component because of the lattice collisions. And near the center of the trap, we get some region where we have a plateau because of combination of the polyblocking and the strong interactions. So this is the half-filled region here. And I'll be focusing all the data. I want to show you all the data. It comes from this half-filled region. So there's probably some very interesting physics happening in the presence of doping and field. But we haven't studied that carefully. So we'll look at this region, and in this region, the polarization, which is this gray curve, is also constant. Okay. So now, one challenge with this microscopy is that actually you get the density, modulo 2, because of the lattice collisions, but you also lose the spin information. And the reason for that is because during this Raman cooling, you're trying to collect thousands of photons, and within the first few photons, optical pumping processes jumble up the spin. Okay, so you lose all spin information very quickly. And so the trick to get spin information is to, before you do the Raman cooling, you first shine a resonant pulse of light to eject one of the spin states. Let's say you eject the majority or the minority, and you get a picture of the minority spins or the majority spins. Or you could take a picture where you do nothing, and you just get the total number. And by taking many shots of such pictures, we can actually build up correlations of the spin in our measurement basis, what I call the SZ correlations. Or if I do a pi over 2 rotation with a radio frequency pulse that rotates the hyperfine states into each other, you can get correlations along in the plane orthogonal to the field. So I'll call these the SX correlations. Okay? So the kinds of pictures we get are something like this. So here's one where we've blown one of the spin states. You can see if you look closely here in this region, there's a little checkerboard kind of order. So that's a little patch of antiferromagnet there. You wouldn't expect to see antiferromagnet everywhere. So first you have to remember this antiferromagnet is only stable close to half filling. So we'd expect it somewhere in this region. But even in the half-filled region, you wouldn't expect checkerboard order everywhere because there's a lot of quantum and thermal fluctuations. So even if you were at 0 temperature, the maximum spin correlations you'd get for nearest neighbor sites is about 30%. So you can roughly get, maybe one way to think about this is the Niel vector can point in any direction at once, and only when it lines up with your measurement basis, then you would see the antiferromagnetic order.
But now that picture is the result of...
This is a single shot.
Well, that's a single shot.
Yeah,
okay.
And we have to take a lot of such shots to get the correlations. Okay, so let's first start by looking at the nearest neighbor correlations. Got my pointer tangled up. Okay, so here are the nearest neighbor correlations, which in the antiferromagnet you would expect to be anti-aligned. So you get negative correlations. And so let me start first by looking at what happens at 0 polarization. Okay, so here's a spin-balanced gas. And there you get, because of this SU2 spin symmetry, the correlations are roughly equal within the error bars. Okay, so the blue and the yellow the yellow is correlations as z along the field, and blue is correlations orthogonal to the field. So we'll call them the SX correlations. And you see here that because of the SU2 symmetry, when the gas is spin balanced, the correlations are about equal. Now, once you start to spin imbalance the gas, you'd expect the correlations to, in the limit of fully polarized, you would expect no correlations, right? There's no more super exchange going on. Okay, so the interesting thing is in between, the correlations along the field die much faster than orthogonal to the field. So this is evidence, starting to look at this canted antiferromagnet, that the correlations prefer to live in the plane orthogonal to the field. So we could, of course, look at also other distance correlations. So let's look at, instead of the nearest neighbor, let's look at the diagonal correlations. So those are shown on the top. The correlations on a diagonal, you expect them to be positive in the antiferromagnet. And indeed, we do see them positive, and they exhibit the same sort of behavior. The correlations die out faster along the field than orthogonal to the field. So from these kind of spin correlations, we can actually extract the temperature of the gas. They're a very good thermometer. So at the temperatures we're working at, we can actually still do quantum Monte Carlo calculations to calculate the spin correlations. And the exact temperature depends on the polarization. Our evaporation, the efficiency of the evaporation depends on the polarization. But we can see that the temperatures we get are in the range of 40% to 60% of the tunneling. These are those fits that these curves that we're using where the temperature is a fit parameter. Okay, one interesting thing I'd like to point out here, because it'll come back, you'll see it again in a different guise later, is this flipping of the sign of the correlations for the diagonal correlations beyond some polarization. So usually you'd expect the diagonal correlations, the spins have to have positive correlations. They're aligned. But actually, here you see they switch to negative beyond some polarization. And we understand that, so you can take the picture there is that you want to imagine, let's go start from the fully polarized limit. If you now start to flip a few spins by reducing the spin polarization, you get a gas of magnons, which are hardcore bosons. And those will have liquid type correlations if they're, so essentially the correlations will be negative for distances below the interparticle spacing. Okay, so that's the reason for this. Okay, so you can see this, they switched to blue essentially. And now, of course, we're not restricted to just looking at nearest neighbor or next nearest neighbor. We can just look at any distance correlations. So these are these checkerboards you're seeing here. So this is for a spin-balanced gas. The top row is for correlations along orthogonal to the field, and the bottom row is correlations along the field. So you can see here, roughly, the correlations they look similar. The range is about 4 sites or so. Now we can get even colder, so the range has increased even more. Okay, so the interesting thing, again, you see that as you increase the polarization, let's say we look at 50% polarization, the correlations are predominantly orthogonal to the plane as opposed to along. Okay? So it's clear evidence for this canted structure. Okay, so I think that's all I wanted to say about this part. Is there any questions?
So if you're not perfectly at 1 atom per site, right, then the fact that you can't measure up and down in the same shot, like, does this give you any errors in how you calculate the correlations?
Yeah, so this is why we take 3 pictures, actually. So you're right. When you have doublons and holes, you can't just use these 2 pictures. So we take a third picture where we measure without removing either spin state.
Right,
and
but you do it in a different experiment, right?
Yeah, there are 3 different. Like, we can just take.
This way you can reconstruct everything.
Yes, if you're just looking at the expectation value of SZ correlations, you can actually show that these 3 types of pictures, you can combine them in a certain way, and you can get exactly the spin-spin correlations.
But each picture is destructive, and then you start over.
Yeah, we just keep repeating, and we take an average.
Because your disorder is static.
Hopefully, we don't have any disorder.
So then
Yeah.
Like from one of the pictures, they suppose to just measure the red.
Yeah, essentially these correct for Doublon hole fluctuations. This kind of picture allows us to correct the Doublon hole fluctuations you're worried about. And it comes out, you can work it out, and it comes out that we can, a linear combination of the expectation values of the particle hole. We can only measure particle hole in the pictures. We can't measure spin states. And a linear combination of these different particle hole correlations at some distance gives us the spin-spin correlations. Yeah.
So what is U and how can you vary it?
What is U, the interaction strength?
Yeah.
It's a contact interaction that arises from van der Waals interactions.
Yeah, I mean the number, U over T.
It's in this case is about 8.
It's about it. Okay. Like if you reduce it, does the exchange go, like do the correlations get stronger or?
We're working at 8 because that's where we expect the strongest correlations.
I see.
Yeah.
So, but are you using a fetchback resonance?
Yeah,
to
yeah. So we can control
set
that.
Yeah.
Mm-hmm. Yeah.
And that's based on theory? Like Monte
Yeah,
Carlo?
based on the Monte Carlo, it peaks roughly at our temperatures around 8.
And how does the answer compare to Monte Carlo? Because this half-filling Monte Carlo should be quite
Yeah, I mean, okay. Well, we're using the temperature as a fit parameter, so we can. I mean, once there's a single fit parameter, but all the curves kind of match.
Oh, okay.
Yeah.
After you.
Yeah.
Now, could you just advance a few slides? There was, okay, here.
Yeah.
Now, the shaded regions, I
Yeah.
take it well, what are the shaded regions?
Well, they're not error bars so much. The error bars are those things
Sure, the
here.
error bars
But
are
what I was saying is that the temperature, as you can see, we can't use a single temperature to fit everything. It seems like when the gas is more polarized, we need a hotter temperature to fit it. So what I'm saying is the temperature range here is between 0.4 and 0.57. It seems as when we prepare a more polarized gas, the evaporation is not as good as you might expect because there's less collisions, and then it's harder to thermalize in the more polarized gas, so the temperature ends up hotter.
Okay, so I'm still not clear. What are the points versus the
Points are the data.
Yeah, but
This is a curve that would be a constant temperature of 0.4.
yeah.
This is a curve that would be a constant temperature of 0.57.
Okay, and the points are assuming a temperature, or?
No, the points are just measured spin correlations. Here, the theory assumes a temperature.
Okay, I see. So okay, fine.
So that's the Monte Carlo. That's what I missed.
Yeah.
Okay, fine.
That's
Yeah, the lines are the Monte Carlo. Yeah, the lines are the Monte Carlo. Yeah, the points are the data.
Okay.
Is the temperature, are each of these samples locally determined from time averages, or do you adjust the total number to get the local polarization variable? I.e.,
These are local polarizations.
I see, so that would imply a temperature that would vary across the sample?
No, the system is in thermal equilibrium. The temperature and the field, because we're in thermal and chemical equilibrium, the temperature and the field are constant across the sample. The temperature we're getting from this fit to the Monte Carlo, and the polarization we're just getting from averaging over many shots and just measuring the local polarization.
What I mean is the disagreement, the fact that it agrees better with a lower temperature at the lower local polarization.
Yeah, this is what
Polarization data is taken nominally within the same sample, just spatially in a different position.
No, they're actually just, I mean, we can't, we're always working at half filling. So we're looking at some density, fixed density in the trap. And then we have to prepare different spin polarizations. So it's not the same cloud.
Okay.
Yeah, and this is why, like here we seem to agree better with this 0.57 is what I'm saying, and here we seem to agree better with 0.4. So that's why I'm saying the temperature seems to depend on how we prepare, like on the spin polarization through the preparation, through the evaporation.
So is it obvious the polarization should be uniform to the cloud?
The polarization is not uniform in the cloud, as I showed you before.
Oh,
This is a local polarization in the half-filled region. So if you recall, the polarization is fixed in the half-filled region, but then it actually goes up towards the edge because of the reduced body blocking. Okay, so now I want to switch to a seemingly different story. Okay, so we're going to switch from repulsive interactions to attractive interactions. and look at an attractive Fermi-Hubbard system, and we'll forget about spin imbalance. So let's just study a spin balance system. Let's first think about what we might expect to see there. Well, now you have attractive interactions between the fermions. So you might expect, okay, if you go to low enough temperatures, they'll pair up, the up and the down. And maybe if you go to a low enough temperature, they'll form an S-wave superfluid. Okay, so this is a 2D system, so there's probably going to be a BKT transition. And as a function of U over T, you might expect a BEC-BCS crossover, just like the BEC-BCS crossover people studied in non-lattice systems in the bulk using Feshbach resonances. Here, again, you get actually a BEC-BCS crossover. So at strong U over T, you get a Bose-Einstein condensate of hardcore bosons, so local pairs on the sites. And if you go to weak interactions, low U over T, you get a BCS superfluid at low enough temperatures, which now the pairs are momentum space. Okay, so let's see what changes in the presence of the lattice. So in the presence of the lattice, the critical temperature for this transition from just pairing to a superfluid has an interesting dependence. So here we're going through this critical point. So when you have a vacuum, or on the other end a band insulator, obviously the critical temperature has to go to 0. And we have particle-hole symmetry, so the whole curve is symmetric. But you might expect that the superfluid temperature might peak around here. But actually, we know from theory it actually dips to 0 right at that point, the critical temperature. And the reason for that is that there's a degeneracy in the system. There's an emergent SU2 symmetry. So there's a degeneracy between a charge density wave and a superfluid ground state in the system. Okay, so when we started looking at this system, the first thing people hadn't studied attractive systems so much. So we thought, okay, the first thing we'd like to know is what is the temperature of our system? How low can we go? So we want a good thermometer. And the natural thing that comes to mind is maybe we can look at pairing correlations in the system, like precursors to superfluidity. But then these kind of things we can't measure with a microscope, right? Those are kind of phase correlations. So what would be more easy to measure is these charge density wave correlations. Okay, so what these look like is essentially you would expect correlations where you have doublons and holes in the system on a checkerboard. Okay? And those are density correlations, so those are probably easier for us to measure. The first thing, the problem you run into is, of course, this is all like pairing physics, so you're looking at doublons mostly. And I told you doublons just disappear during the imaging, so we'll just be looking at mostly empty pictures. So we had to learn how to get around that. So we had a little trick to get around that. So we're preparing, say, our atoms in 2 hyperfine states, which we'll call 1 and 3. These are the lowest and third lowest hyperfine states of lithium. So usually, okay, so you have these 2 atoms on a site, up and down in an attractive pair, and you shine some resonant light, they disappear due to light-assisted collisions. But these light-assisted collisions, of course, depend very strongly on the density. If you're able to reduce the density, then the rate will go down a lot. So the trick we used is to use a radio frequency pulse to flip one of the spin states. Let's say we flip 1, this red atom, into 2, this green atom. And this radio frequency pulse we can do this transfer in a way that resolves the interactions. Okay? So we can essentially only flip this red atom to a green atom only on doubly occupied sites. So essentially, with this way, we tagged the doubly occupied sites with a green atom. And in the process of this flipping, we actually choose our magnetic field so that we go from an attractive pair for these 2 spin states to a repulsive pair for these 2 spin states. And the repulsive pair, now the atoms want to sit far away from each other. And so now if we just blow away this blue spin, we can do that without touching the green one, without doing a light-assisted collision. So essentially, wherever we see a green atom, we know that we had a doublon on that site. Okay? Okay, so now we can do this with about 90% fidelity, this process. We did a test on a band insulator. So usually a band insulator, so here we have this cloud where there's a band insulator in the center. So you have on almost all the sites an up and a down spin. And So here it appears mostly empty in the center. This is conventional image, quantum gas microscope images. This is what it would look like. But then if we do this process, we can make one atom per site, these green atoms, in the center where the band insulator used to live. And you can see this plateau in the center indicating the band insulator. So from these kinds of pictures, we can back out a fidelity of about 90%.
So doing this, looking at pictures, I can't immediately tell, is it better to be looking at the presence of green atoms, or is it better to be looking at the absence of any atoms?
Yeah.
So what's the deal?
The deal is I want to look at now charge density waves, where I need to distinguish doublons from holes. And in the old picture, doublons and holes look the same.
Sure.
So here you can only see the singly occupied sites.
Right.
Is
Yeah.
there a way to generalize this pi over 2 trick, to kind of solve the same problem here?
To rotate the basis.
Right, because here you have the same problem. You can't measure both.
Yeah, we've been playing with that. I mean, it's kind of like not easy because now you need to rotate between 2 atoms and 0 atoms. And there is a way that goes back to Eugene's papers. Like you need to. There's like an eta mode that you can, with some Bragg pulses, you can do something. But yeah, that's a different story. I don't want to get into now. Okay. So here, yes, we won't be able to measure, the equivalent of the XY correlations. Okay. So now we can measure the doublons. So we can measure correlations between the doublons. And indeed, they come out to be on a checkerboard. So this means, like, for example, for nearest neighbor, you're unlikely to find, if you have a doublon, the most likely thing is to find a hole next to it rather than another doublon. And on a diagonal, you're more likely to find another doublon. So here they are now plotted, but now I'm going to plot them versus density. So now I'm no longer restricted to just working at half filling. I'm looking at any filling. So you can see that these correlations are strongest at around half filling. So here are the doublon correlations for the nearest neighbor, and here along the diagonal. And of course, they're negative for the nearest neighbor, and along the diagonal, they're positive. And as you go away from half filling, turns out that the pairing correlations, the superfluid correlations, become stronger, and the doublon correlations are actually are much weaker compared to the pairing correlations, which we can't measure. Okay, so one interesting thing to show here versus density is that if you look at the diagonal correlations, which are supposed to be positive between the doublons, there's this change of sign below some density. Okay, so this is very reminiscent. This graph is very reminiscent of what we saw in the first part of the talk, where we looked at spin correlations in the repulsive system versus polarization, and we saw this behavior, and now we're seeing it again, but with a completely different system, attractive interactions, looking at doublon correlations versus density, and you see the same sort of behavior. Okay?
Are they the same 2 temperatures, or these are no different temperatures for the Monte Carlo?
These lines,
Yeah.
they're at, okay, so this is reminiscent, as I said, because the interactions are different. Here we're working at -6. The temperatures are similar. They're slightly hotter for these things, which is why the correlation length is shorter. Currently in the lab, we can, like this is all data, we can get to 0.3 T in both systems. This seems where we're stuck right now.
Now, I noticed that the points, particularly looking at the diagonal neighbor correlators, the ones that are close to the correlator being near 0 also have very small uncertainties, so you can actually tell that they went negative. So I wonder, did you take a whole lot of data there?
Yeah.
Just to make sure that it was really
Yeah,
negative?
yeah.
Okay.
The statistical error bars are small.
Okay.
Yeah, so haven't we heard the story before? Yes, we have, and there's good reason why these two stories are very similar. The reason is that there is actually a nice mathematical mapping that is very well known between the attractive and the repulsive Hubbard model. So you can actually use something called a partial particle hole transformation to map the operators in the Hubbard Hamiltonian. And if you perform this operation, what it does is it switches the sign of the interactions in the Hamiltonian. So you go, say, from repulsive to attractive or vice versa. And in the process, you swap the role of doping and spin imbalance, the 2 flip roles. Okay, so what used to be in the first story spin imbalance here becomes doping in the attractive case. So the whole phase diagram is very symmetric. So for example, the Mott insulator maps to preformed pairs. The antiferromagnet in the first story has two kinds of spin correlations. We can have correlations along the field or orthogonal to it. Here in the attractive case, the equivalent things are pairing correlations mapped to the XY antiferromagnet, while the charge density wave maps to the Z correlations of the antiferromagnet. Okay? So we have this very nice symmetry, and just to drive this home, I put those two curves next to each other, and here are the pairing correlations from Monte Carlo, which we can't measure, these green ones. And you can see that they're very nice and symmetric. And as a matter of fact, these pairing correlations are always stronger than the charge density wave correlations. So the fact that we're measuring charge density wave correlations actually tells us that implicitly, indirectly, it tells us that we do have S-wave correlation, pairing correlations, precursors to superfluidity in the system. Okay. All right. So in the last 5 or 10 minutes, I want to switch from equilibrium to dynamics. So far you've seen that in all this equilibrium stuff, we can do the Monte Carlo calculations. We're at temperatures that are like pushing the limits of these calculations now at 0.3 T. It becomes really hard to do these calculations, but we're still, we're still able to do them. But once you switch to dynamics, there the calculations become really hard, okay? Almost, we can reach temperatures which you can no longer do the calculations exactly at. Okay, so, but before we go, maybe, I don't want to do out of equilibrium dynamics. Let's just do linear response dynamics, which is still a bit more under control. And in particular, I want to show you here how we can get bad metallic behavior out of a Hubbard system. Okay, so before I tell you what a bad metal is, let me tell you what a good metal is. Okay, so a good metal is one typically where you have weak interactions. And in the presence of weak interactions, you can use Fermi liquid theory and describe the system with quasi-particles. And if you combine that with the Boltzmann equation, you can construct a theory of transport in these weakly interacting systems. So here are some of predictions from Fermi liquid theory. So if you look at the resistivity, say, of a metal with Fermi liquid theory, then as you go to low enough temperatures, the resistivity scales quadratically with the temperatures. This comes purely from interactions. If you go to higher temperatures, you can get a linear scaling from phonons, but we don't have phonons in our lattices. So we expect this T squared from Fermi liquid behavior. Another thing that you could ask is what happens when you no longer have quasi-particles, okay? Say you have strong enough interactions or high enough temperature that quasi-particles are destroyed. Okay, so there's a bound on the resistivity. So if you increase the temperature of something like copper more and more, then eventually you find that its resistivity saturates at some temperature. And the reason this happens is, well, it's not the reason this happens, but this happens at a point where this quasi-particle picture breaks down. Essentially when the de Broglie wavelength becomes small compared to the mean free path, okay, at high enough temperature. That's what people call the Mott-Ioffe-Regel limit. That's the resistivity saturates there. Okay, so now so basically a bad metal is something that violates these things, okay? So at strong interactions and high temperatures, we can't use this Boltzmann theory anymore. And we don't have many good tools for transport. All we have is hydrodynamics on sufficiently large length scales. And these bad metals, what you find in experiments is that they violate the MIR limit. They just go through this bound. They completely ignore the MIR bound. And often you see a linear in temperature resistivity that's not coming from phonons. Okay? Okay, so we set out to look at transport in the Hubbard system and see if we can see some of this phenomenology. And there's been some work looking at transport in cold atoms, in particular from the Esslinger group. So there they try to mimic what you would do in a condensed matter setting. So you can like make some reservoirs, connect them with a channel, and try to measure currents when you apply a voltage or sort of a difference in the potential between the reservoirs. But there usually you end up measuring properties of the channel because these systems are very small. So if we were looking for a way to measure bulk transport, okay? So what we came up with is a way to measure transport coefficients, but through the diffusion constant. So what we did is we have our cloud, and we put a modulation of the density on it. And we looked at how this initial density modulation would decay with time if we just snap off the potential that's creating the density modulation. So from that, we can extract a diffusion constant, and we can relate it to a resistivity or a conductivity through a Nernst-Einstein relationship. Okay, so the Nernst-Einstein relationship tells us simply that the conductivity is the charge susceptibility or the compressibility times the diffusion constant. So this charge susceptibility is something that people know how to measure for a long time in cold atoms. You just say put a gas in a harmonic trap and look at how the density varies with position. You take the derivative and you get the compressibility. But the diffusion thing is the harder part, the diffusion constant. So that's what we wanted to measure. Okay, so to make our system clean, what we did is we don't want to have this annoying harmonic trap. So we actually put this, we flattened the potential in this region. So we have this nice spatial light modulator that allows us to project arbitrary light patterns onto the atoms. And so we have a flat potential in the center. And on top of that, we have a very tiny modulation, a long wavelength modulation of the potential. Okay, so you get the sinusoidal density variation. And okay, so now we just switch off. We keep the flat trap here, but we switch off the modulation and watch how this modulation decays. Okay? So here's what we see. So we can vary the wavelength of the modulation. At long wavelengths, it just decays. We find that the amplitude of the modulation decays exponentially. And then at shorter wavelengths, we see a bit of an underdamped oscillation. So we've done this at, again, this U over T of about 8. The doping is about 17%. So for the cuprates, this would be close to the conjectured quantum critical point. Okay? And so what we can now try to fit these to a simple model. And the simplest model we can come up with that reproduces this behavior is just these two equations. So you can put charge conservation, okay? And the other thing is you can see that you need some sort of inertial term to get this underdamped oscillation. So we added a current relaxation term. So essentially what this equation says that in the limit at long, when you have a steady current, this reduces to the diffusion equation, J equals minus D gradient N. And so this happens with a time scale given by this relaxation time. Okay? So these pair of equations give you the equations of essentially a damped harmonic oscillator. And we can fit all the curves with this kind of form and back out a diffusion constant and gamma. Okay? So here's what we see. So we've looked at this versus temperature. As you might expect, as you lower the temperature, the diffusion constant goes up. And the other ingredient you need to measure the conductivity is to look at the compressibility. So we've also measured that. And at high temperatures, there's a prediction that the compressibility has to go like 1 over T. So we express it actually as T times the compressibility, so that this at high temperatures has to look like a flat line, but we actually see it's varying. So that means we're not in the high temperature limit. So you can see that we're in some sort of intermediate temperature regime where both the compressibility and the diffusion constant are varying with temperature. Okay? So this is not the typical regime people study in condensed matter where the compressibility doesn't vary so much in temperature. Here, both things are varying with temperature. And now here's the interesting part. Both the compressibility and the diffusion depend on temperature. But if we now extract the conductivity or the resistivity, somehow the two magically combine to give you a straight line. Okay? And this is something that, as far as I know, I mean, it's there from numerics also, but we don't understand analytically why this comes about. Okay? So we can, okay, so here's the resistivity. Here's the MIR bond. You can see we're going through the MIR bond. This part is not so surprising going through the MIR bond. That comes actually from the compressibility behavior, the thermodynamics. But the linear part is, as far as I know, is still a mystery. And we can do calculations to see how well this agrees. So these are now calculations with no fit parameters at all. The temperature we back out from the spin correlation stuff I told you earlier. So we've compared to 4x4 exact diagonalizations. We can do those down to a temperature of about 1 with, before the finite size effects start to kick in. And we can also compare to approximate theories like single-site dynamical mean field theory. And of course, that's an approximation, so that has strong deviations from the data, but we can see that the exact diagonalization in the region where it converges seems to agree pretty well with our data. Okay.
In DMFT, can you get the diffusion constant and the compressibility separately?
No. When the DMFT, you get the conductivity directly. So the way you would do it in DMFT is you would compute the current correlations. So this is linear response. You can use a Kubo formula, essentially of this form. And you can get from the current correlations the conductivity. From the density correlations, you get the compressibility, and then you have to back out the diffusion constant. It's the opposite way to what we do in the experiment.
Okay, but they can compute the compressibility.
They can compute the compressibility and the conductivity, but not the diffusion constant. I mean, like, you can do sigma over.
But does the
Yeah.
compressibility that they calculate agree with your measure?
Yeah. Those curves I was showing earlier, those are calculations here. And compressibility is an easy thing. We can do that's equilibrium, equal time correlations. That we can do with QMC, NLCE, lots of theoretical methods. It's really the unequal time correlations that are the headache, and that's where the lowest temperatures we can access with exact techniques are this one, while the DMFT, which seems to have deviations, it can access lower temperatures, but there's a huge approximation, the DMFT approximation. Okay. So I think I don't want to get into this because I'm running out of time. Let me just conclude here. Okay, so I've showed you experiments which have looked at both equilibrium and dynamics. In equilibrium, we're able to reach temperatures where we're pushing the numerical techniques to the edge. We're reaching temperatures of about 0.3, where the quantum Monte Carlo starts to get really hard. But I think we're also getting towards the edge of the experiments. Maybe we can cool further, but we'll have to come up with new ideas there. But I think what's really exciting is now to switch, even at our temperatures, from equilibrium to dynamics. And you can see even linear response dynamics, where theory is still possible to do with this Kubo formalism, we're already getting to temperatures below what you can access with exact techniques, and you can start to test approximate techniques like DMFT. And once you go to out of equilibrium, there really isn't much theoretically that you can do, right? Like besides the exact analyzations. Okay, so with that, I'd like to just thank the members of my group. So Deban, Peter, and Elmer are the graduate students who've done these experiments. Stan and Peter Schaus are postdocs. Peter will soon be starting as a faculty at the University of Virginia. And we've had the support of many theorists for all these numerics we've done. In particular, I'd like to thank David Hughes at Princeton and Yuri and André-Marie Tremblay, who've worked a lot on this calculations of the conductivity. And thank you very much.